Section 9.5, we're changing gears here and talking about polar coordinates. So what we'll talk about is plotting points and finding multiple representations of points in the polar coordinate system, converting points from rectangular to polar, and then back, and converting equations from rectangular to polar and then back to rectangular. So representation of graphs of equations as collection of points, the x comma y, in the rectangular coordinate system where x and y represent directed distances from the coordinate axis to the point xy. So what that's really talking about is that's just what we're used to, where we have everything's x or y. We go horizontally x, we go up and down y, and that's the rectangular coordinate system. So we're actually going to talk about a new system, a new coordinate system in this section called the polar coordinate system, and that's all based on circles, almost like the unit circle, but it has all of the same angle measures around it, but it's not the unit circle because the radius of the circle doesn't have to be 1. So we could have multiple circles. So to form the polar coordinate system of a plane, what happened is we fixed a point O on the pole, which is called the origin. So this point right here is always on the origin, and construct O from an initial ray called the polar axis as shown in the figure. So if you were to rotate around an axis for some distance, and then this line we would say is R, which is really like if you were to kind of go around in a circular way, that R value would be the radius of your circle. And any point on that circle in the polar coordinate system, we would have R, which is just the radius of the circle that you're on. And theta would be how far you've gone from the polar axis. So each point is assigned a coordinate, R and theta. R is the distance from the pole, so the radius of the circle, and theta is the angle, the counterclockwise from the polar axis. So we're going to first just plot a couple points here and talk about why they're plotted where they are. So the first point, 2 pi over 3, remember 2 is your R and pi over 3 is your theta. So when we construct these polar coordinates, you have all these circles, and your first circle would have a radius of 1, your second radius 2, third radius 3. So when R is 2, what you would do is you would count out 2 from the center, so you would get to there, and then you'd have to rotate pi over 3 along that second circle till you get to this point. And so that point right there, no lines or anything else. So if you were plotting the point 2, 3, you would just put a point right there. So you will have to remember all of those different angle measures from your unit circle. On the next one, if we're plotting the point 3, negative pi over 6, remember 3 is your R, negative pi over 6 is your theta. So you would go out 3 and then rotate negative pi over 6 until you get to that point right there. So the third point, 3, 11 pi over 6, if you notice, if we went out 3 to here, and then we went around in the positive direction 11 pi over 6, that gets us to this point, which was the same as the previous one, which was 3, negative pi over 6. So what you find with polar coordinates is if they're, remember when we went back to coterminal, if they're coterminal, they're going to end up on the same spot on the polar axis, which is where this next slide talks about that with rectangular coordinates, every point is specific and unique. But with polar coordinates, they can be written in multiple ways, but still represent the same point. So if we had the point r theta, it would be the same as if we had the point r and then theta plus 2 pi, right? If we just went one full rotation around, we'd get back to that same point. Same thing if you had r theta. If we did negative r, so if we, instead of going positive 2, we went negative 2, and then we only went around pi from or did theta plus pi, we would still end up at the same point. So you just have all these different representations of how to get to a point. And the pole, anytime your r is 0, you'll just be at the origin or the pole of that coordinate or that polar coordinate system. Theta could be anything there. All right, so let's plot the point 3, negative 3 pi over 4. So if we go out 3, that takes us to the third circle. Negative 3 pi over 4, so we'd be at negative 1 pi over 4 here, negative 2 pi over 4 here. So negative 3 pi over 4 would be right here. And I'm going to erase those other points so that's not going to confuse us. So that's 3, negative 3 pi over 4. And we have to come up with some other ways to write that point. So our R value, we could go still positive 3, or we could go out here, but instead of going in a negative direction, we could go in a positive direction. So instead of going negative 3 pi over 4, we could say we could also get there by going positive 5 pi over 4. That would be one way. Or we could go count out negative 3. So if R is negative 3, and then we could go, again, this is still positive. So to get from this point at negative 3 to this point right here, we could go positive pi over 4. Or, because I think it says 3 additional points, we could do another negative 3, but we could go in the negative direction, right? So here we could go all the way around to here, which gets us at negative 7 pi over 4. So those would be 3 different ways that you could represent that same point. And then the coordinate conversion. So if you have an x and a y coordinate, it really just matches right up with that polar grid. So your r theta coordinates with the point x and y. And so these formulas will hopefully look familiar from previous chapters. So if we need to find theta, if we're given x and y, we're going to use the formula that the tangent of theta equals y over x, and that r squared equals x squared plus y squared. So that's if we need to go from rectangular to polar. That would be if we're given, so this would be if we're given x, y, and we want to, and we need to find r and theta. The other is polar to rectangular. So polar to rectangular would be that we're given r and theta, and we want to find our x and our y. Right, so if we're given r and theta, to find x, we'll do r cosine theta. To find y, we'll do r sine theta. And if you take a look at your formula sheet, you'll see that those equations are on there for you. So you don't need to memorize them, you just need to be able to use them. So example 3, we're going to convert polar to rectangular. So they tell you this is polar, which means that your r is 2 and your theta is pi. And so if we want to go polar to rectangular, then that means that we need to find x and we need to find y. And remember, for x, we're using r cosine theta. And for y, we're using r sine theta. So to solve for x, we'll do r is 2, and then cosine and theta is pi. And if we can write these as exact values, you need to leave them as exact values. So we get 2 times negative 1. So our x coordinate is negative 2. When we plug our values into y, we get 2 times the sine of pi. So we get 2 times 0. So our y coordinate is 0. So our rectangular coordinate, our x, y, would be the point negative 2, 0. Which, if you think about it, if you were to graph on a polar coordinate system the point 2 pi, so you'd have the 2 circles, and we'd go out 2 and around pi, we would be here. And on a rectangular graph, does that represent the same place if you graphed the point negative 2, 0? They should fall in that same location. So equation conversion is a little bit more difficult. So point conversion from polar to rectangular is pretty straightforward. You use the formulas. To convert a rectangular equation to polar form, you're going to replace the x with r cosine theta and a y with r sine theta. So if you needed to convert this equation right here, y equals x squared, into polar form, we need to get rid of x's and y's. So we know that y is r sine theta, x is r cosine theta. And if we were to simplify all that, we would get secant theta tangent theta, and that would just be using our trig information that we have from before. So let's look at these three equations, and we're going to convert them back to rectangular. So we need to get rid of the r's and the thetas. But first, let's graph them, because sometimes by graphing them, it can help you recognize what the equation should be. So first, if we're graphing r equals 2, that means theta can be anything, but r has to be 2. So if you start thinking about, well, r is 2 here and here and here, and really it's anywhere on this second circle, r would be 2. So if r is 2, right, it's a circle. And remember, when we have our equations, we know that r squared equals x squared plus y squared. So if we need to get rid of the r, we could think of this equation, and I think this is actually on our next slide. We could think of this equation if we squared both sides. So we'll move on to our next one. So if we squared both sides, we would get r squared equals 4. And from this equation that we have, instead of r squared, we could say then that x squared plus y squared equals 4. We could do that substitution. So let's look at this next one. Theta equals pi over 3. So they don't tell us what r is, so that means r could be anything, but our theta has to be at pi over 3. So if r is 1 and theta is pi over 3, we'd be here. If r is 2, we'd be here. R is 3, r is 4. Same thing in the other direction. So we would have all these points, which means that this r equals, oops, sorry, that line's not good. If theta equals pi over 3, we would have this line that goes through your equation. So to convert this one, we have a theta. So we're going to use our equation with our theta. Remember, tangent of theta equals x over y. But they gave us theta, so let's go down to this next slide here. So if they gave us theta, and we're using the tangent of theta equals x over y, then what we know is that the inverse tangent of x over y has to equal theta, right? And do we know what theta equals? Yep, they told us it's pi over 3. So what happens then is we know that the inverse tangent of x over y has to equal pi over 3. And so if we go back to that, if we kind of go backwards, then we know then that x over y has to equal the tangent of pi over 3. So again, using that unit circle knowledge, we know that the tangent of pi over 3 is the square root of 3. Oh, sorry guys, it's not tangent x over y. Go back, it's tangent y over x. We're going to fix that before we write it all down wrong, which you probably already did, but we're going to fix it. So we're going to go tangent of theta is y over x, y over x, y over x, because it will make a difference in this final equation. Right, so then if we solve for y, we get y equals root 3x, which is a diagonal line with a slope of root 3 through the origin. And if we go back up here, and if I fix this one, y over x, that's that line, though, that we graphed. And then part C is pretty tricky. If you just have r equals secant of theta, you might not really be able to graph it. So with that one, let's first convert it. And remember, though, we know that we're using, if we have secant, think back to your relationships and remember that cosine of theta is 1 over secant. So secant and cosine go together, which means we're probably going to use that r cosine theta equals x relationship here. And so if we do that with our equation, we could rewrite our equation as r equals 1 over cosine of theta instead of saying secant. So we could say that r times the cosine of theta equals 1. And we know that r cosine theta is x. So this is really just the equation x equals 1. And so if we were to go back up and graph it, where x is 1, so we're at that first circle, and x equals 1 is a vertical line. So you would just draw a vertical line through your graph.